Welcome to the Deep Dive. Today we're taking a plunge into a construction material that's really shaking things up. Cross-Laminated Timber, CLT, these are incredibly strong modern timber structures, and they're pushing boundaries. I mean, buildings up to 18 stories tall.
It's pretty amazing.
And a huge part of that, a really critical part, is understanding something fundamental. How does CLT actually perform when, faced with fire?
Right. It's the key question for safety.
So our listener, they've armed us with some deep research. We've got everything from fire resistance ratings, the nitty-gritty details, to the complex engineering calculations behind it all.
Yeah, there's quite a bit there.
Our mission, then, is to sift through that, pull out the key insights, the real aha moments.
Yeah.
So you can walk away with a really clear understanding of how these impressive timber buildings are designed to be safe and, robust. Okay, so let's start right at the beginning then. When we talk about a fire resistance rating for building materials, what does that actually mean? What are we measuring?
Well, at its core, a fire resistance rating tells you how long a building component could be, a floor, a wall, a beam, whatever, how long it can maintain its structural integrity and do its job when it's exposed to a standardized fire.
Standardized fire.
Yeah, and these ratings, they're not just guesses. They come from really rigorous testing. The gold standard, certainly in North America, and it's what our sources focus on, is ASTM E119 testing.
ASTM E119. Okay, I'm looking at the time temperature curve from that test in our sources now, and wow, it shows temperatures just rocketing up. Nearly 2,000 degrees Fahrenheit in, 180 minutes, 3 hours? That's intense.
It absolutely is. It's designed to simulate a really severe building fire. So, okay, in construction, you need to prove these ratings, right? They need to be formally demonstrated.
How do you do that?
Our sources lay out two main ways, two pathways. One is pretty straightforward, using tested assemblies. Basically, you use building parts or systems that have literally been put through these intense fire tests, physically tested and passed.
Okay, that makes sense. Use what's already proven in the lab.
Exactly.
Yeah.
The second pathway, though, is through analytical methods. This is where the engineers really earn their keep doing the calculations.
The math part.
Sort of. Think of it like this. You either use something physically tested or you go this analytical route. And this analytical approach isn't just one thing. It's more like a toolbox of different methods.
Okay.
You might use a design that's already pre-approved based on standards. Or you could follow specific prescriptive designs laid out in the building code, like in IBC 721.
IBC being the International Building Code.
Correct. Or you perform detailed calculations, which is IBC 722. You could even do engineering analysis based on other tested assemblies or propose alternative methods, or get a design certified by an approved agency. There's a whole list.
Wow, okay.
It's all about rigorous proof, you see. But there are multiple ways to provide that proof. You can also use supplementary evidence like test reports from approved labs, UL listings, things like that.
So it's not just one test, it's this whole system of verified methods, all backed by solid science. And for our deep dive today, we're really zooming in on that calculated fire resistance rating of exposed timber, how engineers use those detailed calculations.
Exactly. That calculation path, specifically referencing the National Design Specification, or NDS.
Which brings us to something I found honestly pretty fascinating and kind of counterintuitive about wood and fire. The idea of charring. Wood forms this protective layer when it burns. How does that work, especially with something layered like CLT?
It's actually one of wood's really incredible natural defenses. Oh. When timber gets exposed to intense heat, the outer layer burns, right? Yeah. But it forms this layer of char.
Okay.
And this char layer, it acts as an insulator. It protects the unburnt wood underneath it. This is step one in how we calculate fire resistance, figuring out the calculated char depth.
Gotcha.
The National Design Specification, the NDS, it recognizes a kind of standard or nominal char rate of 1.5 inches per hour for wood products, including CLT.
1.5 inches per hour.
Okay.
And this is where it gets really interesting and maybe surprising. The actual calculated char depth, which engineers call a CAR, it's non-linear. Non-linear. What does that mean here?
It means it doesn't just burn inwards at a steady 1.5 inches every hour. The formula they use is a char 1.5 T 0.813. That is time in hours.
Okay, check to the power of 0.813, less than 1.
Exactly.
Yeah.
Which means the char rate actually slows down over time.
It slows down.
Yeah. The deeper that char layer gets, the better it insulates the wood underneath. So the fire progresses slower and slower into the wood. It's like the wood is building its own shield, and that shield gets thicker and more effective as time goes on.
Huh. So wait, Does that mean a thicker piece of CLT might give you, like, disproportionately more fire protection than a thinner one? Just because that slowing down effect has more time to, take hold.
That's a fantastic insight. Yes, absolutely. That's exactly right. The thicker the lamination, the longer the charring process has to slow down, the better the insulation. It's a key reason why those thicker CLT panels perform so well in fire tests.
Wow.
Now, with CLT specifically, because it's made of layers, right? Layers glued together.
Right. Cross-laminated.
The char rate is assumed to kind of restart at each glue line. Yeah, think of it like hitting a reset button. As the fire burns through one lamination and reaches the glue and the start of the next layer, the char rate effectively jumps back up to that initial faster rate for that new layer before it then starts slowing down again within that lamination.
Wow. Okay, so calculating the total char depth for a multi-layer CLT panel sounds tricky then. With this nonlinear rate and the restarts, how do engineers actually do that?
It definitely requires a systematic approach, yeah. But the logic is pretty neat. First, they figure out something called flagy. That's the time it takes for the char to burn completely through one single lamination. The formula involves the lamination thickness, SLAM, and that standard 1.5 inch per hour rate raised to a power of 1.23. That exponent, the 1.23, that's derived from tests to account for the nonlinear behavior.
Okay, makes sense.
So our sources give examples. For a thin, say, 58-inch lamination, TD is about 20 minutes. But for a thicker 138-inch lamination, TD is much longer, almost 54 minutes.
Big difference.
Huge difference. So once you know TG for your lamination thickness, you figure out, okay, for a given fire duration, say 2 hours, how many full layers will char completely? That's on lam.
On lam, number of layers.
Right. Then you calculate how long that takes. Then you see how much time is left in your total fire duration. And then you calculate how much char forms in that last partially charred layer during that remaining time using the nonlinear formula again.
Phew. Okay, that's several steps.
It is. But you combine all those pieces to get the total depth of a char at time TD. The formula looks like a char in Cesso, it's on lam plus 1.5, TGMO 0.813.
Okay, I see the parts there. Number of layers times thickness plus the partial char in the last layer.
Exactly. So plug everything in, and the total char comes out to 3.159 inches.
3.159 inches. Okay.
But wait, there's one more little adjustment. That's the visible char. Engineers then calculate what's called the effective char depth, or EFDF. Yeah, a 4F is slightly larger. It accounts for a thin zone of wood just beyond the visible char where the heat might have slightly degraded the wood's strength even if it hasn't turned black. It's a bit of a safety factor.
Okay.
It's calculated simply as a 4F equals 1.2 a chart. So you multiply the visible char by 1.2. For our example, a char was 3.159 inches. So a 4F becomes 3.791 inches.
Almost 3.8 inches. That's a decent bit more than the visible char.
It is. And it's that OCRF number, the effective char depth, that's used in the next step for the strength calculations. It's a more conservative, safer number for design.
Right. And I did see that in the NDS for unequal layer thicknesses, use a spreadsheet, which really tells you, yeah, these aren't simple lookup values. You need specialized tools, real engineering software, or spreadsheets to do this properly, especially if the CLT layers aren't all the same thickness.
Absolutely. It gets complex quickly.
Okay. So once we know how much wood has effectively charred away that sort of protective sacrifice, you could say the huge next question for the engineer is, what's left?
Right.
How much strength does that unburnt core of the CLT still have?
Oh.
Which leads us to step 2, capacity of the unaffected depth.
Exactly. What's the remaining strength?
Yep.
For this, engineers typically use what's called the shear analogy model.
Shear analogy model.
It's a recognized method to calculate the bending and shear capacities of the remaining section of the CLT, the part that hasn't charred, based on that RF depth we just figured out. This model is pretty sophisticated. It can be adapted for different CLT layups, whether the layers are arranged symmetrically or if it's an unbalanced layup, which changes where the neutral axis, the point of zero stress, sits inside the panel. The model gives you a single bending capacity value that works for both directions of bending.
So engineers aren't always doing this completely from scratch by hand, right? They're using these verified tools.
Correct. These tools are essential for efficiency and accuracy, especially with the complexity involved.
Which brings us neatly to step 3. Compare adjusted capacity to applied design loads. This is the check, right? The demand versus capacity check. Does the remaining wood have enough strength for the loads it still needs to carry during the fire?
That's the bottom line. This is the demand capacity ratio, or DCR, check under fire conditions. For bending, you're essentially checking, is the applied bending moment, less than or equal to the calculated fire-rated bending capacity.
Right.
And there's an interesting factor applied here. The allowable capacity is multiplied by a stress increase factor, 2.85, which comes from the NDS.
2.85. Why the increase?
It recognizes that a fire is an extraordinary short-term event. Wood can actually handle higher stresses for short durations compared to long-term loads. So the code allows you to use this higher temporary strength in the fire check. Makes sense.
Okay. That does make sense. A temporary boost for an emergency situation.
Exactly. And there's a similar, slightly different factor, 2.75, used for the shear check. So you compare the applied shear, VA, to the adjusted shear capacity.
Got it. Compare demand to the boosted capacity.
Right. And our sources give some really practical insights here. For instance, take a common 5-layer, 678-inch thick CLT panel. If it needs a 2-hour fire rating, the checks often show that bending in the main direction is the critical thing you need to worry about. This might be true even if the panel looks perfectly fine under normal non-fire loads, maybe with a DCR around, say, 35%.
So, okay, in normal use, but fire is the bigger challenge for bending.
Often, yes. But now, consider that same panel, but you only need a 1-hour rating. In that case, bending and shear might not be controlling at all. Why? Because less time means less char. The effective char depth after 1 hour is much smaller, maybe around 1.9 inches instead of the nearly 3.8 inches we saw for 2 hours. Less wood lost means more remaining strength.
Okay, that difference between 1 and 2 hours is huge in terms of remaining material.
It really is. And there's another example for a thinner 3-layer CLT needing a 1-hour rating, where the calculation might even simplify down to just checking a single layer acting like regular lumber.
And there's that specific real-world example in the sources too, right? The one that ties the load, the CLT grade, and the fire rating all together. Can you walk us through that one? It seems really telling.
Absolutely. It's a great illustration. Let's picture a floor spanning 15 feet. Pretty typical. And let's say it has a dead load, the weight of the structure itself, of 75 pounds per square foot, PSF. And a live load, people, furniture of 50 PSF.
Okay, 75 dead, 50 live.
You run the structural analysis, and this setup creates a bending moment, of 516 pound-feet per foot. Pound BFTFT. That's the demand on the floor.
3516. That's the target the CLT needs to meet.
Under load, yes. Now let's look at a 678-inch thick V3 grade CLT panel. V3 is a common visual grade. In a non-fire scenario, just everyday use, its demand-capacity ratio is 0.88.
0.88. So it's working pretty hard, close to its limit, but technically acceptable, right? Less than 1.0.
Correct. Acceptable day-to-day. But now let's apply the 2-hour fire resistance calculation to it. We calculate its remaining strength after 2 hours of fire exposure using the char depth and the stress increase factor, and its fire-rated capacity drops dramatically, down to just 4,136 pound FD.
Wow, only 1436, but the demand was 3516.
Exactly. 1436 is much less than the 3,516 pound FD demand. So even though that V3 CLT panel was okay for normal use, it would not be sufficient for the span under 2-hour fire conditions. It would fail.
That's a huge difference. Okay.
Now, let's compare that to a different grade of CLT. Same size, 678 inches thick, but this time it's an E4 grade CLT. E grades are based on stiffness properties, generally stronger and stiffer than V grades.
Okay, E4 grade, same size, higher grade.
We run the same 2-hour fire calculation for the E4 panel. Its fire-rated capacity comes out to 300 and 735 pound-feet of heat.
9735. Okay, and the demand was 3516.
Right. 3735 is greater than 3 and 516. So the E4 grade CLT is acceptable for this scenario under the 2-hour fire condition.
Okay, so the higher grade makes all the difference in the fire scenario.
It absolutely can. And interestingly, the E4's non-fire DCR is also much lower, only 0.34, so it has more reserve capacity even in normal use. But the critical point is its fire performance. And here's the practical takeaway. Those E grades of CLT. They typically cost more than the V grades. There's a cost premium. So this detailed fire analysis isn't just about safety. It's crucial for cost-effective design, too. You need to know if the standard V grade is enough, or if you must specify the more expensive E grade to meet the fire code for that specific situation.
Wow, that V3 versus E4 example really drives it home. It shows how these, seemingly small details in the calculations and material grades translate directly into massive differences in performance, safety, and cost.
Precisely.
We've covered a lot of ground today, from the basics of fire ratings and that intense ASTM E119 test, through the really fascinating science of how timber chars non-linearly.
The slowing down effect.
How engineers calculate that char depth through multiple layers, accounting for the glue lines, getting to that effective depth.
Right, the EDIF.
And then finally, how they assess the remaining strength and do that critical demand versus capacity check, considering those stress increase factors.
Yeah, bringing it all together.
Just knowing about that nonlinear char, the glue line restarts, and especially seeing that stark difference between V and E grades under fire, it gives you a much, much deeper appreciation for how these modern mass timber buildings are engineered to be so safe and resilient.
It really does. It highlights just how sophisticated these engineered wood systems are and how many different factors have to be considered to ensure that structural integrity during a fire. So maybe a final thought for you, our listener. When you consider these specific, sometimes kind of hidden details like the char rate not being constant or how much the lamination thickness matters or the grade differences, what other questions pop into your mind? What further things might we need to explore about really optimizing material choices, balancing that absolute need for safety with making these sustainable buildings cost-effective? It's a field that's definitely still evolving.
That's a fantastic question to ponder. We really hope this deep dive has given you a solid grasp of CLT fire design. Thanks for joining us, and we hope you'll join us next time for another deep dive into the fascinating world of information.